Hello everyone, welcome to COMP382. In this video we are going to continue our discussion about finite automata, and today we are going to focus on non-deterministic finite automata. Remember this question from last week, a language of binary strings containing the pattern 110110. We have actually seen how to create a DFA for this language. This is the result. Okay, I'm going to show you another finite state for this machine, which looks completely different. I shouldn't say probably completely different, but it looks different than the other one. What do you think about this finite automaton? Is it a finite automaton at all? Is it a deterministic finite automaton? And if it is a finite automaton, how does this machine work? What type of strings, which strings can be actually accepted by this automaton? So clearly this is not going to be a DFA, but yes, it is a finite automaton. It has a finite number of states and it has some transition between them, but it is not a deterministic finite automaton, and you can actually understand that by looking at a state Q0, and you can see that for from Q0 there are two transitions for one, so it makes it a non-deterministic finite automaton. We have talked about the deterministic finite automaton, and we have seen that in deterministic finite automaton, at each situation you can be only in one state, but the difference between DFA and NFA is that in NFA it is possible that at some situations you can be in more than one state. I mean, some of the actions are non-deterministic. Later on I will explain that how the machines, how the non-deterministic finite automaton accept the language, and what does this mean when we say the machine can be in more than one situation. Okay, let's just now answer this question, that how does this machine work? If we pass a string to this machine, how the machine check if the string is going to be accepted or rejected. Okay, look at this example here. Let's actually just try this example over this machine and see that what we can get. Okay, for the first actually symbol, which is going to be 1, if you look at, we will start from the first state, right? State Q0, which is marked as your starting state, and the first symbol here is going to be 1, and here you actually got this at this position, that what should I do? Should I go with this transition and stay at Q0, or should I go to Q1? The thing is, you should actually choose. If you have more than one, if you have an NFA, if you have more than one transition, just choose one of these transitions. I'm going to just show you this example, then later on show you what are the different possibilities that we can get. Okay, here assume that I am staying at Q0 for the first symbol, so it's just like you are actually following this transition and stay at Q0. For the next symbol, still we stay at Q0, we choose to stay at Q0. It is possible, right? The machine allows you to stay at Q0. If for the next symbol, again, wait at Q0. For the next symbol, wait at Q0. For the next symbol, which is 0, if you are at Q0, you have to stay because there is no other transition here. For another one, you have two options. You can either stay at Q0 or go to Q1. This time, we choose to go to Q1. Okay. For the next symbol from Q1, there is exactly one transition, so we go to Q2. At that position you see a 0 in the input, so we have to go to Q3. At Q3 we see a 0. What would happen? The machine doesn't show any transition, which means that it will crash, and so this string will be rejected. By this set of choices that we made, this string is going to be rejected. But what if I choose a different set of choices? What if when I saw Q0, when I saw the first one at Q0, I stay at Q0. For the second one, I stay, but for the third one, instead of staying like the previous choice, here I'm going to go to Q1 instead. I will go to Q1 with the next symbol. From Q1 we go to Q2. With the 0 from Q2 we go to Q3. With the next symbol from Q3 we go to Q4. With the next symbol, which is again 1 from Q4, we go to Q5. With the next symbol, which is 0, we go to Q6. And this time we reach to a final state, and the transitions here allows us to stay at the final state, right? So for the next two symbols, you stay at Q6, which is a final state, and you are reading the full string and you accept the string. So by this set of choices, this time the same string will be accepted by this machine. So which one is correct? Are we going to reject the string or we are going to accept the string? The property of the NFAs is that for any input string, if you can find at least one way to reach to a final state by reading all of the tokens in the string, you will accept the string. Okay, so if there are plenty of different set of choices that you can make, and all of them are going to reject the string, but there is one path, one set of choices that will end up to an accepting a state, you are going to accept this thing. It doesn't matter that for all of the other ways you are going to, the machine will reject it. It doesn't matter. If you can find one way to reach to an accepting a state by reading the whole string in an NFA, you are going to accept the string. This actually kind of makes the designing the NFA a little bit tricky. In some way, designing an NFA is going to be easier than DFA, but it is going to be kind of more error prone as well. Okay, you will actually get used to the idea. But let's just get back to this example, and let's just take a few minutes and think about this. The language which is accepted by this NFA, and which is basically the same language here, and why we actually think that this is going to be the language of this finite state. This, you can see that this is different than the DFA, the first DFA that I showed you. But the thing is, the language of this machine is going to be exactly all the binary strings that has the pattern 110 and how we can actually prove it? Either we can go with the inductive approach that we have discussed for the DFAs. You can basically just almost the same approach that we discussed last week. You can follow the same approach here to show that it's going to be the language of this NFA. But here I'm going to give you, some more intuitive, informal way to prove that this is going to be the language of the NFA. If you think about this NFA, first, to actually prove that this is going to be the language of the NFA, I have to do two parts. I have to prove that the machine is going to accept all the strings in this form, And I have to also show that all the strings in this form will be accepted by this. This machine is not going to accept anything else, anything except than this set of strings. So the first part is that the machine accepts all the strings in this form. Okay, so all the binary strings that you have, which has the pattern 110110, if the pattern is in the string, it means that you can divide the strings to three parts. You can divide the strings to actually some part which is x, the part that where the pattern actually happened, and the rest of the strings you can actually assign it as well. So in this way I have divided the string to three parts. The pattern, wherever the pattern actually happened, actually the prefix before that, and the suffix after actually the pattern. Okay, so if you have a string like this, you have a string that has the pattern, you can divide it in this way. So for the part which is going to be the x, you can, using actually this transition and this state, it's clear that you can stay in Q0 while you are reading the x part of the string, right? And then when the x is done, you can actually read this pattern and follow exactly this pattern in all of these states and reach to Q6. And when you reach to Q6, you can consume and read the suffix of the strings, the y part, and by reading that you can see that this transitions allows you to stay at Q6, and so this machine will definitely accept all the binary strings which has the pattern 110110. And the machine doesn't accept anything else. The machine doesn't accept more than this set of binary strings. The reason is that if you have a string that doesn't have the pattern 110, there is no way that you can reach from Q0 to Q6. For any binary string that you pass it to this NFA, definitely you will start at Q0, right? And the only path to a final state is going to actually pass through this path, right? And the transitions over the path clearly shows the pattern 110110. Okay, so definitely all the strings that are going to be accepted by this NFA should have the pattern. Okay, so kind of you can see that NFAs are actually some way to design a finite automata for the regular languages that tries to abstract away the details. As you can see here, we care about the pattern 110, and the NFA just basically just cares about the pattern 110. It's, the whole idea of designing the NFAs is that we abstract away the details of the implementation and just say that, okay, what I want, not what I don't want. When you are designing a DFA, we care about all the states, all the transitions, and we show what the machine needs to do in every possible situation. When you are designing an NFA, we just care about the what we exactly want. We don't show the those things that we don't want. So when you are designing an NFA, later on I'm going to show you that NFAs and DFAs are going to represent the same set of languages. Both of them are going to represent regular languages. So they have the same expressive power. But kind of designing NFAs are supposed to be easier for us, and they are going to be similar to the idea of backtracking. So I'm going to show you some more examples, then we come back to this idea. Okay, so here is an example of an NFA for a language that accepts strings with the pattern 1 1. Again, you can see that this is very similar to the previous example that we see. If I care about the pattern 1 1, what I do is that I just created one starting state, actually a couple of intermediate states, and show all the pattern that I need. For example, 1 1 here, so I just need 2 more states and a final states, and in the starting state I will just consume all the 0 ones before the pattern, and at the final state you again just consumes all the 0 ones after the pattern. So kind of whenever you are designing an NFA for for some languages that just care about a specific pattern, this is the way that we actually designed an NFA for them. You can see that it's much easier than designing a DFA. Okay, design an NFA that accepts this language, all the binary strings that this time starts with 0 0, not just having the pattern. So designing an NFA for this one again is going to be very easy. So you can actually start with some state Q0, and the thing is here I don't actually put allow any other transition here except the transition 0. So in this way I am forcing the strings to start with a 0 and start with actually the pattern 0 0 1, and then after that it actually end up to a final state, and you can actually stay here for all the other binary strings. Designing a DFA for this one is also easy, but here I just wanted to give you the idea. Okay, let's see another example. All the binary strings that end to the pattern 0 0. Again here, when you are actually caring about this type of strings, it's just like I allow the Q0 to consume the X part, okay, and then I will create some path that ends to an accepting state. And be careful, here I don't actually put any transition for Q2. So basically, if you, for any string that you pass to this NFA, if the string has the pattern 0 0, it is possible to reach to Q2. But if there is still something after that, you cannot actually read more than that. So look at an example like this to make it more clear. So look at a string like this one. Okay, someone might actually say that this string will end up to Q2. That's right, this string will end up to Q2, but you cannot actually consume the whole input string and stay at Q2. What would happen here is that for the first symbol, you can say that, okay, I will go to Q1. For the second symbol, you can say that, okay, I will go to Q2, right? And then you have the input symbol 1 that remain, and you have to read it. If you read it from Q2, there is no transition for 1. So this machine is going to reject the string. This machine is going to crash. There is no transition at Q2 for 1, and so this machine is not accepting the string. And that's correct because the string will not end to 00. Okay, so another example, what does this NFA accept, or what is going to be the language of this NFA? If you get an NFA, basically just like what you do for the DFAs, here you just need to figure out which type of strings will be accepted by this machine. You can see that here all the strings that actually have the pattern 0, 0 will end up to a final state, right? Not only that, there is one more path that started from Q0, it ends up to an accepting state, and that's going to be this path, right? So all the binary string that has the pattern 0, 0, or so basically all the binary strings which are in this form or in this form will be accepted by this NFA. So this is going to be all the binary strings that either contain the pattern 0, 0 or 1, 1. So now let's formally define the NFA. The definition is kind of very similar to DFA. Again, we have a 5 tuple. We have a set of states, just like DFA. We have an alphabet, which is going to be a finite set of states. Just be careful, the number of states should be finite, exactly like the DFA. We have one starting state. We usually show it by Q0. We have a set of accepting state. And we have a transition function. The main difference between the DFA and NFA is in the transition function. The transition function of DFA was actually a mapping from the states and the symbol of alphabet to the states, okay? But here in the NFA, this mapping actually goes to a set of states. So for each transition of, for example, if you are at a state you are at a state Q and you see a symbol S, it is possible that you go to more than one state. In the DFA, you exactly go to one state. In the NFA, it is possible to go to more than one state. So here is an example of showing the NFA using a transition table. So whenever in the transition table you saw a sum of the cells in the table shows more than one state, it means that your finite state is going to be an NFA, not a DFA, which is clearly here. It is an NFA because you have more than one transition of 1 over Q0, one of them here and one of them here. Okay, this one is another example showing you that, for example, Q0 has more than one state in the transition table over 0, both 0 and 1. So let's just actually review a couple of facts about the NFAs. For some of the transitions, you might not actually have any state in the NFA. NFA doesn't actually show all of the information. This property is something which is not only in the NFA, in the DFAs as well, we do have this property. This is, just a representation thing. So it doesn't show that your finite state is going to be an NFA if it doesn't show a transition for a state. But some things which are specifically just for the NFAs is that the transition at a specific state and a specific symbol can actually go to more than one state. The other thing about the NFAs is that if you are going to accept a string in an NFA, it is enough if you can find one set of choices, one path that starts from the starting states end up to one of the final states, an accepting state. You are going to reject a string if you cannot find any path starting from the starting state to one of the accepting states. And the language which is accepted by an NFA is going to be the set of all strings which are going to be accepted by that NFA. This is again similar to what we have for the DFAs. So Now let me actually just discuss about this fact that how NFAs are going to work. If you have a DFA, everything is clear. You can simply, if I give you a transition table, you can simulate what the DFA does, right? You can even write a program to simulate what a DFA does. You just need to basically implement, you just need to store the transition table of a DFA, because DFA express everything, all the computation, right? You have a transition table and you just read the input string one by one, read each character, each symbol in the input string, and just check the transition table. You keep the current state, check the transition table. Okay, this is the input token, this is the state. Where should I go? You just update the state, the current state, and go on. But in the NFA, everything is different, because you have to just search for one possible path that end up to an accepting state, and there might be millions of different paths. How we can actually simulate NFA? How does NFA actually work? NFA is, as I have a couple of times explained this, NFAs don't have more expressive power than DFAs. They are not going to have more computational power. They have exactly the same computational power than DFAs. So every string that can be accepted by an NFA can be accepted by a DFA as well. The difference between an NFA, the difference between NFAs and DFAs is that NFAs just abstract away the details. Okay, they don't show what we don't want, so they don't show everything. They just express what we care about, what we want. Okay, so kind of this is similar to what we do when we are writing a search algorithm that works in a backtracking way. Okay, so when you write down a search algorithm, if you pass them AI course, when you write down a search and you have a backtracking, you are searching for something, right? And whenever one of the branches in your search reaches to a point that there is no answer, you just backtrack and go back and look at the other options. Okay, let me show it to you using an example. Assume you have an NFA like this and you have an input string like this one. How you are going to check if the string is going to be accepted or not? Just think about it, that you are writing a program to simulate the NFA. Okay, not only as a human, but how you actually think that if you find a path here or not. The thing is, you can simply just conduct a search, a complete search. Just try to search all of the possible paths, and if we can find one path to Q2 by reading the input string, that's enough to say that the string is going to be accepted. So what would happen here? Starting from Q0, you start reading the input string. From Q0, by reading the input symbol 0, I can see that there are two transitions, there are two possibilities for me. I can either go to Q1 or stay at Q0, okay? So I will represent both of these states. I will say that, okay, at Q0, I can either go to Q1 or stay at Q0. I am going to show all of the possibilities. So let's first follow and actually continue on the first path. If I could find a path, that's enough. Otherwise, I will backtrack. At Q1, by reading the next symbol, which is going to be 0, I will see that, okay, this path is not going to grow anymore. It's just like I got stuck here. The machine is crashed, right? So I cannot actually continue. What should I do? I will backtrack. It's just like you will undo this action, go back to Q0 and say that, okay, let's go back and actually follow another path. again, it's just like, no, I am at Q0. I know that I cannot follow this path. And I will say that, okay, by reading the first symbol, I know I'm going to actually just follow this path. Say that I will stay at Q0 this time. Then what would happen if you stay at Q0? In the next actually step, I'm going to read the next input symbol, which is going to be 0. Again, at Q0, I have two options, right? I can either go to Q1 or stay at Q0. Okay, so now you can see that at this situation, again, I'm just representing both of the possibilities. Either stay at Q0 or go to Q1. At Q0, if you stay at Q0, if you read the next input symbol, this is going to be 1, right? And with the transition 1, there is only one possibility. You have to stay at Q0. And so you are going to end the input string. And you will see that, again, this path is not going to accept the string. This path is rejecting the string. So what should I do now? This is one of the paths. Still, I have some other possibilities, right? So it's just like in your search tree, what I have actually represented here is going to be like a search tree. Although I have showed it in a horizontal way, you can show it in vertical way as well. But anyway, this is going to tell me that this path is not successful, so I will backtrack. I will go back to here. Do I have another option, another choice here? No, I don't have. So I will backtrack to here. So do I have another option? Yes, I can follow this path. So it's just like I will backtrack, and here I will follow the other actually option that I have. Maybe there I can reach to an accepting state. When I am backtracking to this situation, it means that I have just read the first input symbol, right? And then with reading the next input symbol, I am going to go to Q1. And let's see that what would happen here. At Q1, and I am here. I have actually one more input symbol to read. Then this state is going to, from Q1, by reading 1, I can go to Q2. And yes, this path end up to an accepting state for me, right? So I'm going to accept the string. Basically, if you wanted to really create a machine that represent this NFA, your machine, by reading the input string 001, has to do all of this computation. What has been represented here is basically a search tree. Your machine needs to do all of this computation. So NFA just abstracted all of everything, every details. Although if you wanted to make a machine that does the computation, the machine needs to do all of these computations. So although designing NFAs might look easier, but the machine that do the job basically needs to probably do more computation than the corresponding DFA. If you create a DFA that accepts the same language, because DFA makes the computation much easier. In the DFA, you don't have more than one path. Whenever you read a string, the DFA exactly tells you what to do. If I had a DFA for the same language, for example, if I create a DFA for the same language here, that's going to be something like this. Q0 with 0, it goes to Q1. Q1 with 1, it goes to Q2. This is going to be the language of all binary strings that ends to 0, 1, right? All binary strings in this form. Okay, that ends to 0, 1. So if I create a DFA for this language, it's going to look like this. If you see a 0, it goes back to here. If you see a 1, it goes back to here. If you see a 1, it will stay. Okay, this is going to be a DFA corresponding to the same language, which represent the same language. If I give this a string to this DFA, what does the DFA do? Q0, the DFA reads as 0, so it just goes to, with a 0 it goes to Q1, with the another 0 it goes to Q, sorry, with another 0 it stays at Q1, with the next symbol, which is 1, it goes to Q2. Okay, so you can see that if you have a DFA, basically you only have one path. But if you have an NFA, you need to do the full search. You need to do all of this computation here. Let me show you another example. I'm going to have the same NFA, but another string. So you know that this string is going to be rejected because the NFA is going to accept all binary strings that ends to the pattern 0, 1, and we don't have that pattern at the end of the string. Okay, so let me actually show you that how NFA will understand that the string is going to be rejected. Again, we have to do the full search here. You start from Q0, and you should actually represent the full search with the transition 0. There are two possibilities: either you stay at Q0 or go to Q1. In this path, you will go to with the next input symbol 1, you will stay at Q0. There is no more than one option here. At Q0, again, you will see the input symbol 0. There are two options, either stay at Q0 or go to Q1. Let me actually complete this path from Q0. By seeing a 0, you have two options, either stay at Q0 or go to Q1. You can see that this path is going to reject the string, right? So I will backtrack here and then follow the other path. This path is going to reject the string. Q1 is not an accepting state, so you will backtrack, and then you will, let me use a different color. You will backtrack here, and then you will backtrack here. Then this time you will follow this path. From Q0 you actually go to Q1, but again at Q1 you can see that the next input symbol is going to be 0, and you are rejecting the string because there is no transition of 0 over Q1. So this path is going to be rejected. So you backtrack from here, and then there is no other option to check at Q0, you backtrack. There is no other option at Q0 here, you backtrack. Here we follow the other path. By reading a 0, we go to Q1. At Q1, by reading a 1, you go to Q2. And then here, you still need to actually read two more zeros, right? But at Q2 there is no transition, and so this machine is going to crash at this path as well. So we couldn't find any path to accept the string. This string is going to be rejected. If you, in the previous example, if I draw the DFA, again you can see that instead of having a full search tree, it's just going to be a straightforward approach. You started from the starting state and just follow all the transitions in the DFA, and you reject the string. So kind of, if you design a DFA, the computation is going to be less. If you design an NFA, the design is easier, but the computation is going to be more, because you need to do the full search over the search space to say that the string is accepted or rejected. Okay, so let's see another example. Designing an NFA that accepts all binary strings in this form. A couple of zeros followed by a couple of ones. that the number of zeros, the number of zeros and ones, both of them are going to be greater than 1, but there is no relationship between them. So you can have any number of zeros and any number of ones greater than 1. So this is going to be an NFA that accepts the machine. You first consume all the zeros, then you go to the Q1, then consume all the ones, and just go to Q2, which is going to be an accepting state. Another example, build an NFA that represent the language of binary strings. All the binary strings where the third symbol from the end is going to be 1. So it actually just means that at least the length of the string is going to be 3, right? Because it's saying that the third symbol from the end. So all these strings are going to be in the language. You see that in all of them, the third symbol from the end is 1. Okay, to draw an NFA for this type of strings, basically the pattern is very easy. I can, again, just create a starting state that consumes. You can just say that this is just like you consume everything, and then say that, okay, having a pattern like this 1, which is going to be the third symbol, still I need to create 3 more states to reach to Q1, Q2, Q3, and I make this one an accepting state, and I allow to have these symbols to be either 0 or 1. I don't actually care, both of them will actually end up to Q3. The only thing that matters is that this transition, which is going to be the third one from the end, is going to be 1. So kind of this is a pattern to design an NFA for this type of languages. Okay, just as an exercise, I would actually I would like you to try to think about a DFA. Create a DFA for accepting the same language. When you are writing the DFA for accepting the same language, you will see that how many states the DFA needs and how complicated the DFA can be comparing to designing an NFA. And you will see that why we really care about the NFAs. When we are designing the NFAs, the only thing that we care is that, am I able to create an NFA for this language? Basically, the thing is that I would care that if the language is a regular language or not. Basically, NFAs are going to make life easier for us when we want to determine if a language is regular or not. When you are doing this exercise, you will see that sometimes designing the DFA is going to be very complicated, although designing the NFA is going to be much easier. And you don't actually really care about creating the DFA or NFA. The only thing that you care is that, can I create a finite state? Is this language going to be regular or not? So if I can create an NFA for that, I will say that, okay, this is going to be a regular language. So NFA, designing NFAs makes the, solving this problem much easier for us, that when you wanted to determine if the language is regular or not, if you can create an NFA for that, you will say that, okay, this is going to be regular. And NFAs designing, I just wanted to say that designing NFAs are going to be much easier, and basically helps us to understand some properties of the language. If the language is some simple in terms of simple, I mean something that the creating a machine to accept it is going to take less computational power. So let's just actually leave it here, and because we are going to actually continue our discussion about regular languages for at least 2 more weeks, and I will just talk about this more, that how to actually recognize if a language is regular or not. One way for that is try to design a finite state for that. Okay, so let me here just introduce that notion of the transition function and extension of the transition functions for NFAs. This is exactly similar to what we had for the DFAs. One transition, we know that the transition function in the NFAs can end up to result in more than one state. Okay, you can extend it just like what we did in the DFAs and write it as delta hat, which you pass, instead of one symbol, you can pass a full string to that. Starting from Q0, if you pass this string, where you are going to end up. So this is just basically telling you that just follow all the possibilities and just say that after reading the string 001, in which states we can be. So remember we had this actually this search tree here. Let me just clean up here a little bit. Okay, so I have actually written this one here as well. The thing is, when you read a string more than one symbol, if you start at Q0, okay, after reading 0, you can be in more than one states, right? So the transition of Q0 and 0 is going to be the set of Q0 and Q1. This is exactly what we mean by saying we can be in more than one situation we can be at more than one state at a situation. So you can actually extend this and say that if I started at Q0 and I read, for example, the string 01, where I can be. This is going to be this set of states. You can see that I have, basically if you just create the full search tree and by reading a string and just follow and show all the possible states, it's going to actually answer you this question. This is going to be the set of states Q0 and Q2, right? If, for example, the string is going to be 0, 1, 0, the set of strings, the set of states is going to be again Q0, Q1. So basically, we just wanted to know that which states we can be after reading the full strings, for example, 001, 000, 0, something like that, whatever. Okay, so let's answer these questions. Assume that I have this NFA and I am going to actually answer that where we will end up if we start at Q0 and we read the input string 001. So you can actually start it at Q0 and say that it's just like I'm creating this search tree. You can draw it horizontally or just vertically. Let me here just show it to you vertically. By reading a 0, there are two possibilities, right? You can either go to Q1 or there are three possibilities basically. Go to Q2 or go to Q3. So I'm going to represent all of those paths. You can either go to Q1, Q2, or Q3. And then by reading a 1 from Q1, you have two possibilities. You can go to Q2 or you can go to Q3. From Q2, by reading a 1, you can see that this level represents reading a 0, this level represents reading the 1. From Q2, by reading a 1, there is only one possibility, one transition actually, that ends up to Q3. At Q3, by reading a 1, there is no transition. Okay, so this 1 is going to stop here, or you can represent it in any way. Just show that this is going to, this is not a state. It's just, I'm trying to tell you that if you are at Q3 and you read a 1, the machine is going to crash. So the answer for this question is going to be the set of all the states here, Q2, Q3, and the last one is also Q3. So this is going to be only Q2 and Q3, right? So what's going to be the answer for this one? I have already actually answered this part of it, right? This is the search tree so far. So if I continue and read another 0, I can actually just extend the tree here and say that, okay, if I'm at Q2 and I see a 0, where I will end up? You can see that at Q2, there is no transition over 0. So this one is going to crash, this path. How about Q3? There is no transition over Q3 and 0, so this one is going to crash. And there is no transition for Q3, so this one is going to crash. That's it. So if you see another 0, basically the answer of this question is going to be empty set. So if you see a string like this, this is going to be rejected, or the machine cannot actually continue after this point if you started from Q0.